multiplicative type complex calculus. It is simply abbreviated as MCC. The other conventional calculus will be called as additive type complex calculus, so it will be abbreviated as ACC. So they will be compared in the following parts. Especially the advantages of the new calculus, multiplicative calculus, will be demonstrated. It will, in short time duration, in 30 minutes, it's not possible to show all details. Only a brief summary of the topics will be given. As you know, the calculus arose during the 17th century by the works of Newton, by the definitions of Newton. A new kind of mathematical branch arose, and this led to the development of industrial revolution, and lots of electrical machines and industrial devices arise. Even the calculus is now a branch of mathematics called differentiation and integration. It's used to model natural laws in physics, biology, chemistry, economics, and other fields, often by means of differential equations and also sometimes in the form of integral equations. The main problem is to make estimation of the future from the present and past values of a quantity. This is a simple explanation about the need for a calculus. Why do we need a calculus? If we have a natural quantity, if we have a quantity known today, and if its past value, yesterday value, is also available to us, the issue is to estimate the future. How do we estimate the next value of the quantity? This is done by means of calculus, as you know. And equations, differential equations and integral equations are simply some modeling of natural laws. We see around in the nature, there are some physical laws, chemical laws, biological laws. They are all modeled by some manner, and the issue is to find a differential equation for any natural law. It may be a model, maybe an example of a model is a rabbit-fox system in a forest, the number of rabbits and foxes in a forest. They can be given by a set of two equations, differential equations, first order differential equations. This is an approximation. And using the initial values of these quantities, it's possible to find the number of rabbits and foxes versus the time. Another example is to make analysis of a pendulum system. The angular position and the velocity, angular velocity, may be analyzed by means of a differential equation. This is again in the form of a coupled set of two equations. And even in engineering areas, the heat transfer, the variation of a heat on a metal body, can be analyzed by means of partial differential equations. Let's remember the basic principles of calculus. It was first invented by Newton, as you know, in 1966. And then Leibniz contributed to this definition of the calculus through the integral parts. He defined the integration process. And according to the understanding and the philosophy of the Newton's calculus, we can make a subtraction between the two values of a function, maybe the past value and the present value, and the future value may be estimated by means of this approximation. And the definition of the calculus is known as a limit, given by a limit as the variable parameter h goes to 0. We make a subtraction between two quantities, and this limit is known as the different derivative of the function. And then integration of the area under a curve was considered by Leibniz, and then he discovered this integral operation, as you know. So After these definitions, after defining a differential operator, after making these definitions, there were many contributors, among them Euler and Gauss contributed too much, and also there are lots of other mathematicians. Their names are listed here. After definition, first a differential operator is defined, and then integration operator may be defined, and they are used for making manipulations and for writing differential equations for systems. For example, derivative of z to power n is z to power alpha is alpha times z to power alpha minus 1. And even there are lots of interesting theorems: mean value theorem, Cauchy's residue theorem, Taylor series expansion theorem, Taylor series of a cosine function, or 1 over cosine function. They can be given in these forms. We know all these, and they are called classical calculus. We are very familiar with it. Now the question is, classical calculus is normally based on additive notions or subtraction operation. At the beginning, we subtract the two values of the function, make a subtraction, and then divide with the infinitesimal distance. And this is, so we can say that it's based on additive operation or subtraction operation. But what would happen if the derivative and integrals were defined in a fundamentally different way? This was first proposed in 1938 and further developed through contributions in 1972, 1999, 2008 for real-valued positive and real-valued functions. In 2010, it was extended to a complex-valued functions. This is the first page of this paper. Multiplicative type complex calculus as an alternative to the classical calculus, published in 2010. And it is 13 pages. It's not possible to discuss all issues of this paper here. It's very lengthy. I recommend you to read out these pages. Before starting to a definition, before establishing a calculus, in the initial sections of this paper, I defined two operators, logarithm operator and an exponential operator, denoted by L and L to power minus 1, and also defined a summation operation with a circle with a plus inside in section 2.1. The L operator is similar to the natural logarithm function plus an imaginary part showing the argument value of the argument. And the imaginary part may be understood as a number between minus pi and plus pi. And inverse of this L operator may be understood as an exponential function, as we are very familiar with the exponential function, inverse of this L operator. And then define two sets of numbers. One set of numbers is a complex plane, as you know, the whole complex plane, but 0 is accepted. You see, there is a complex plane that is punctured at the origin. This is the domain of the L operator, and this domain may be mapped onto a strip on the other domain by means of L operator. It is transformed, it's mapped onto a strip. And inverse operator can map any number in this strip into the normal complex plane. And then the definition of the fundamental definition of the complex calculus comes. Assume any function that is an element of the punctured complex plane C minus 0, and assume any complex number, infinitesimal number that is non-zero, and this element of this complex plane, then the derivative of the function may be defined as an inverse operator plus making a subtraction between the two transformed values of the function. This subtraction operation is similar to the definition of the classical calculus, and we have also division. And after applying these operations, we get a derivative of the function. This derivative will be different than the conventional derivative. A careful analysis shows that there is a relation between the normal derivative and the new kind of derivative, this multiplicative derivative. This is a relation. I can show you this. You see the right-hand side of this equation, an exponential function, and the left-hand side is the new definition of the derivative. Therefore, a connection formula between the conventional classical calculus and the new calculus is given by this equality. Any function on the normal complex calculus plane may be differentiated by means of a logarithmic derivative in the exponential part. I mean, this definition is equivalent to the exponential operation and differentiation on the logarithm of the function. A careful analysis shows this. It may be difficult to see at this point, this connection, but in any way, a careful analysis shows this. Therefore, we define a differentiation operator, derivative operator, and integral operator, integration operator. And by this way, the derivative of z to power alpha would be equal to e to power alpha over z, right? Derivative of an exponential e to power alpha z for any constant alpha, it will be e to power alpha. And derivative of integral of z to power alpha, it will be equal to e to power z alpha z ln z minus alpha z times k. This k is an arbitrary constant that should be an element of the punctured z plane. And integral of an exponential function is equal to e to power alpha z squared over 2. Again, k is a constant that should be an element of the punctured complex plane. And this is a short explanation for this new kind of calculus. The remaining parts, I will show you some applications and some comparisons. Let's see the corresponding theorems like mean value theorem in normal calculus, Cauchy's residue theorem, Taylor series expansion theorems. In the mentioned paper, I gave the multiplicative version of the mean value theorem, multiplicative version of Cauchy's residue theorem, and multiplicative version of the Taylor series expansion theorem, and it may be called as Taylor product expansion theorem. For example, the Taylor product expansion of normal cosine function would be e to power minus z squared minus z to power 4 over 12, z to power 6 over 45, and so on. Yes. Is there any question? Okay. The derivative, the Taylor product expansion of cosine function, 1 over cosine function.
Bakarım bir ara İshak Hoca. Şu an bir konferansı dinliyorum, sonra bakayım olur mu? Peki kuzum. Hadi iyi çalışmalar. Sağ ol. Teşekkür ederim.
This Taylor product expansion of this 1 over cosine would be automatically equal to the negative of the previous one. You see here, instead of negative signatures, since 1 over cosine z is multiplicative inverse of the cosine function, it will be very simple to get to deduce the Taylor product expansion of 1 over cosine function. Similarly, sine function and sine 1 over sine z functions may be expanded in this form. You see exponential powers, powers of the variable in the exponential part, and that of the 1 over z would be equal to, can be negative of the multiplicative inverse of the previously obtained Taylor product expansion. Its counterparts in the normal usual calculus will be like, cosine function, sine function. We are very familiar with them. And that of 1 over sine function or that of 1 over cosine function, they can be obtained as given here. You see restrictions when expanding 1 over cosine z function. The argument z should be less than, its magnitude should be less than pi over 2 in complex plane. And that of when expanding 1 over sine z, the magnitude of z should be less than pi. And there is no restriction for the cosine function and the sine functions. Their argument z values may be infinitely large, very large. But they suffer from slow convergence. But their counterparts in the multiplicative calculus, for example, the expansion of cosine function, it has a restriction. Its argument should be less than pi over 2. So it seems the Taylor product expansion of cosine function will be useless because it has a restriction. But in practice, if you try leading terms of these expansion and compare with the same number of terms with the Taylor series expansion, you will see the accuracy of this cosine function is generally better than that of the other conventional cosine function. So they should be used in practice. We cannot be sure about their advantages at this point. Possible applications of the multiplicative calculus that may appear in the future may be numerical solutions of differential equations, interpolation equations for finding intermediate values from table values, alternatives to Taylor, Maclaurin, and Power series expansion, and evaluation of counter integrals, possible applications in the future. For among them, numerical solution of differential equations may be possible. Consider applying Euler's method, well-known Euler's first-order approximation for solving any first-order differential equation. This is the usual formula for a numerical solution. We can use this approximation for the derivative terms and then continue with this by using also the initial value. We can obtain the results. If we utilize the principles of the complex calculus, its solution should be in this form. The new value of the function should be equal to the actual value multiplied with an exponential h times f over yn, and this OH square means the order of the error. This type of example was discussed in the mentioned paper, in my paper in 2010, and it exists as a numerical example somewhere in that book. And here are some numerical results. In a numerical result, I worked with the differential equation of a Bessel function. This is a second-order differential equation for the Bessel function. Its exact solution is known to be a first-order, first-kind Bessel function. And by using a test initial values, I did calculations. I tried numerical solution of this differential equation and compared with the exact solution of the problem. So exact values are compared with the approximate results, and all complex, by working with complex numbers, the variation of the relative errors are obtained as shown in this figure. Along different complex number scenarios, the accuracy, the relative error of the multiplicative scheme mark was small in the first case, in one case study. In another case study, the multiplicative error, these dashed lines, are smaller than the conventional error. So this second case study shows very good accuracy of the multiplicative calculus. And in the third case study, even we observed very good results.
Ya ben yani açtım şeyi şu anda Ali.
We get these accurate results. So in the three different case studies, two of them gave very accurate results. One of them gave, in the first case, the accuracies were comparable. So there was no obvious advantage of the multiplicative calculus in this case. Anyway, it was just an example. It's possible to find counter examples. I mean, some examples in which classical calculus approximations would be better than the multiplicative calculus. Any calculus cannot be perfect. In another application, another possible application may be an interpolation, finding an intermediate value or values from a table values. Consider a table of functions like cosine function. For testing the accuracy, I considered cosine function. The values of this function at different arguments like 2.2 plus 1.5 and 2.2 plus 1.1, their values are known from the table. Then consider a case study. Estimate the value of the function at 2.1 plus 1.3, just at the midpoint between these two complex numbers. How do we estimate it? According to the classical understanding, according to the classical interpolation principle, we can set up this equation, right? We use the two known values, two values from the table, and this z is a variable. By substituting the point under the consideration, we can estimate, we can get the result. And as an alternative to this, if we make the interpolation using the new kind of calculus, multiplicative calculus, this equation should be in this form. This was discussed in the paper in 2010. You look at the similarity. Instead of subtraction, we use the division. Instead of addition, we use multiplication, right? So multiplicative calculus or division of the quantities. And instead of this multiplication, we have an exponential part. So it may give a better accuracy. So their accuracies may be compared by making simple calculations. If we calculate the function and the approximated values at the argument at 2.1, then we get these two results. One obtained according to the additive calculus has an error on the order of 0.0251. If the calculation is made using multiplicative calculus, its error is much smaller, 0.0080. So this example shows that the accuracy of the multiplicative calculus when making interpolation is much better than that of additive calculus. But it's possible to find a counter example. I mean, an extraordinary function, a different function, may when working with a different function, it's possible to see a different situation. This is just an alternative approximation technique is suggested. This color graph shows the image plot of the cosine function, absolute value of the cosine function on the complex plane. The considered points ZA and ZB are the points as indicated spot on the figure. So intermediate value is estimated at this midpoint between ZA and ZB. Another application of the calculus may be Taylor series expansion. For example, Taylor series expansion of 1 over z squared its Taylor product expansion may be written in this form, right? And it is valid. It will be valid in the condition that absolute z is less than 1. According to the classical calculus, this 1 over z 1 plus z square may be expressed in this form. The same condition applies. So what will be the accuracies? In this figure, a comparison is made between the values. In this blue curve is for additive approximation. This black curve is for multiplicative approximation, and this red curve is for exact value. In this figure, we see that the multiplicative approximation is better. It has a good accuracy. There are also possible lots of other examples that can be given. I think we are coming to the end of the time. Let me mention you about some papers that are some publications. It was applied to electromagnetic wave scattering problems. In 2014, this principle, multiplicative calculus principle, was applied when calculating the electromagnetic waves that are reflected or diffracted. There is a diffraction mechanism known in the literature of electromagnetics. Diffracted waves are calculated when making approximation for the diffracted waves. So improvement of the diffraction coefficient of the GTD method by using multiplicative calculus. This is a high impact journal, IEEE Transactions on Antennas and Propagation. Their editors liked the form of the multiplicative calculus. Even I remember one of the editors asked me to include an appendix describing multiplicative calculus for those engineers of electromagnetics. In the appendix of this paper, you can see another short explanation of the multiplicative calculus. So see the appendix of this paper for a brief explanation of multiplicative calculus from the viewpoints of electromagnetic engineers. In 2018, so this is the repeated calculation. In 2018, 2021, 2023, the similar problems, similar approximations are used in these papers. They are evaluations of some class of integrals that arise in wave scattering problems, electromagnetic problems, series expansions that are immune to round of errors for the transition function. So round of errors are considered. I mean, multiplicative calculus principles were used for reducing the round of errors. Evaluation of the remainders of a class of series by using saddle paint method, and also lots of other applications. By saying the transition function, one of the famous integrals that were discussed in these papers is this. The main problem is to evaluate this integral for any x. X may be any positive real number. So for a variable x, evaluation of the integral is an issue in electromagnetic problems. In this type of wave diffraction problems, I mean, this is a boundary value problem. You know, this is called a wedge, and there is a source or initial values, etc. Calculation of the full solution may be obtained by first evaluating this type of integral. Anyway, from the viewpoint of mathematics, evaluation of this integral was considered in lots of my papers, and many times I benefited from multiplicative calculus and mentioned in appropriate places and get these different versions. Those series that does not exist in the literature are as follows. Normally, this series, this does not exist in the literature. First time it was established in one of my papers. And I contributed to the other integral forms in the paper. In another paper in 2014, 2015, 2020, and 2023, I considered this type of electromagnetic boundary value problems or scattering problems. A solution, a color graph of the solution is displayed in this figure. Again, the boundary value problem solutions are obtained from this evaluation of this kind of integral. In this type of problems are a bit complex, and their solutions are according to the evaluation of this integral. H0 in this kind of representation is known as Hankel function, Hankel. In one of paper in 2023, this problem was discussed. And finally, last year in September, I published this paper, Techniques for Obtaining Non-Divergent Series as Alternatives to Divergent Asymptotic Series for Spatial Functions and Integrals. Again, published in IEEE Transactions on Antennas and Propagation. In this paper, I considered evaluations of these two types of integrals. One of them is a line integral. I mean, an integral along the real axis. And the other is this subscript C, means a contour integral. Contour integral. The contour integral has a shape like this. If you are familiar with this type of contour integrals, a contour that starts at plus infinity and then around 0, it swings around 0 and then goes back to infinity. This is also called as Hankel's loop in the literature, Hankel's loop integral. So for arbitrary functions of pi and q, evaluations of these integrals are discussed from the viewpoint of multiplicative calculus. And many spatial functions may be written in this form. Among them, error function, complementary error function, may be written as an integral in the given form. Another integral, another spatial function is the Aries integral. Aries integral may be put into the given form of integral. Another one is the Hankel's function. It can be put into an integral of the given form. For example, that of the Hankel function is given as a counter integral like this. That of the Aries function can be given as an integral like this. So these are the types of integrals that was considered at the beginning of the paper. And the numerical results are obtained in the paper. One of the numerical results are as shown here, the relative errors of the error function. When the calculations are done using the conventional calculus, we get these blue curves, sorry, these green curves. This green curve, the epsilon 1 means when the leading term of the asymptotic series is used. And the other green curves, for example, this last one, E7, means when the leading 7 terms of the asymptotic series are used in the approximation. On the vertical axis, we have the relative errors. You see, the relative errors of the green curves are much higher than the relative errors of the conventional curves. This black curve, continuous black curve, and dashed black curves are for the results that are obtained according to the multiplicative calculus. There are actually the two different techniques were developed in this paper. According to first technique, we get this black continuous black curve. And according to the second technique, we get this dashed black curve. So this figure displays a great accuracy improvement in the results. And in another curve regarding the area function calculations, in another figure, we observe similar situations. The relative errors of the conventional calculus are much higher than the relative errors of the new methods. And I think I am coming to the end of the time. I would like to express my sincere gratitude to Professor Dr. Feyzi Bashar for his encouragement and for his valuable revisions and corrections during the preparation of the initial manuscript in 2010. He is among the listeners. I would like to thank to him. He encouraged me to prepare, and he made revisions when preparing the initial manuscript.